Hello everyone, my name is Iris. Today our group is going to talk about model diagnostics and power analysis. This is the order of what we are talking about and their respective speakers. First, we will talk about model diagnostics. After we construct the statistical model, we want to make sure it aligns with the assumptions that we required. Diagnostics models are ways to check whether the assumptions are satisfied. As for two-sample t-tests, there are three assumptions. First, we assume datasets are normally distributed. This can be verified by using QQ-plot. Secondly, we assume that each observations are independent. If we have correlated data, it will look like there are more samples than we do. Lastly, we assume there are equal standard deviations. The QQ-plot or the normal probability plot could verify whether the distribution is normal or not. The graph shown above is based on a perfect normal distribution. The x-axis is quantile that follows normal distribution, while y-axis is the quantile we generated from the data. We want to compare with each point represent where the data lies on the normal distribution based on quantile. In the example, the first point represents where the first percentile lies on the distribution. The density in the middle will be high to match the peak in normal distribution, and it gets thin around the tail. It is almost impossible to achieve data that follows normal distribution perfectly, but we want to get as close to a straight line as we can. The normal probability plot could also be used in comparing two sets of data. Here is an example from the book. In this experiment, we would like to test the hypothesis that the mean normalized fluorescence after 2 hours is greater for nerve tissue than for muscle tissue. However, as from the QQ plot above, the two sample standard deviations are quite different, so the assumption of equal variances in the pooled t-test may not be appropriate. This plot also indicates that the two population variances are probably not the same. Because the equal variance assumption is not appropriate, we will use the two-sample t-test to test the hypothesis of equal means.
So now let's reinforce our understanding about the normal probability plot with some simulated examples. Before that, I want to point out that the normal probability plot is a special case of a family of plot called QQ plot. And QQ plot is the abbreviation of quantile-quantile plot. And as its name suggests, the x-axis and the y-axis of the plot corresponds to the quantiles of a reference distribution and the quantiles of your dataset, respectively. The reference distribution is not limited to normal distribution, and when the reference distribution is actually normal distribution, your quantile-quantile plot is exactly the normal probability plot. QQ plot is actually a very, very powerful graphical approach, and it has much wider application beyond testing the assumption of two-sample t-test. So here are some examples of normal probability plots under different scenarios. In the middle, we see that all the points are actually lying on a straight line, and that's what you expect to see when your data is normally distributed. When the distribution of your data set is skewed to the left, then you expect to see very small values to pop up more frequently than in the normal distribution. And in other words, more density will be amassed in the left tail. That means the observed quantile at the lower end of your dataset is smaller than expected, and that's why you see such pattern in the normal probability plot. And likewise, when the distribution of your dataset is skewed to the right, you will expect to see larger value pop up more frequently than in the normal distribution. And in other words, the density is actually amassed in the right tail. And the observed quantile at the upper end of your dataset is higher than expected. So you will see an inflation here. With these intuitions in mind, it's actually very straightforward to interpret the shape of probability plots when your data has fat tail or thin tail. Basically, when you have more extreme values in your data set, the quantiles at the lower end and the upper end of your data set will be smaller and larger than expected, respectively. And if your data has greater centrality and thus narrower than the normal distribution, um, the quantiles at the lower end and the upper end of your data set should be greater and smaller, respectively.
Hi, my name is Carly. I'm going to be talking about power analysis. So power is the probability that we reject the null hypothesis given that it is actually false. It's also known as the probability of avoiding a type 2 error, which is when we accept a false null hypothesis. Essentially, you can look at it as the probability that we make the right decision in rejecting the null. Power is denoted as 1 minus beta. So for power analysis, that's when we can use power to determine an efficient sample size for an experiment. What you do is you'd use a power curve, which is where you graph power on the y-axis and sample size on the x, and just evaluate power at each sample size within your given window. And you can see power will increase as sample size increases. So usually what you'll be able to do is find a point where the power maxes out at a certain n. And this can be efficient for us if we have limited resources or a budget, because then we can run, say power maxes out at n equals 20, we can run an experiment at n equals 20 instead of n equals 50 and save time and resources. And then when we use this for difference of means, the greater the difference in means that we have, there's going to be more power as well. So what we need to know to run a power analysis, looking at difference in means here, we need to know population means, the population standard deviations. These values are not often known, so researchers will usually make educated guesses, and they'll also usually vary some of the values to determine the effect. So for example, in difference in means, they'll use different difference in means and see how the power changes with that. So the advantages to power analysis is that it gives us a visualization of power versus sample size, and it is relatively straightforward because you're pretty much just finding out the power, and there's plenty of software that can do this too. But the limitations is that the factors that can affect power are not often taken into consideration, and it can't reflect the complexities that can arise in an experiment. So essentially, it can kind of oversimplify things in a way, but it is still a really useful tool when determining an efficient sample size for an experiment.
Power analysis can be explained by two graphical examples, the OC curve and the power curve. In this slide, I will talk about the power curve first. The horizontal axis is the sample size and the vertical axis is 1 minus beta, which is the probability of rejecting a false null hypothesis successfully. The gray curve has a 0.8 fixed difference in means, and as the sample size increases to nearly 40, the probability of rejecting the false null hypothesis is already very high, approximating to 1. So instead of collecting 60 or even 100 sample size, people can detect the differences in means with only 40 sample size. On this slide, I will talk about another graphical example, the OC curve. OC curve is a graph of beta error versus the differences in means under a fixed sample size. On the right side of this slide is a graph of several OC curves with different fixed sample size. The horizontal axis is the differences in means, and the vertical line is the probability of accepting the null hypothesis. The null hypothesis in this example is mu1 equal to mu2, and when the sample size is fixed, for example, to 2, even the differences in means is increasing to 3, the probability of accepting the null hypothesis that the differences in means equal to 0 is still nearly 0.7, which is quite high. When the sample size has been set to 2, even though we can see the probability of making the type 2 error decreases as the differences in means increases, the decreasing rate is quite small. As the sample size becomes larger and larger to 100, for example, just like the OC curve at the most left-hand side, the decreasing rate of making the type 2 error is dramatic. So, as the sample size increases, people are less likely to fail to reject a false null hypothesis.